curvature, scalar curvature. Basically, some observations regarding total mean curvature and a variational analog of Brownian mass. I must admit that you will soon realize that this talk is the only talk today which is completely Riemannian. So I apologize for that. Let me first give you an outline of the talk.
Just
that'll work. Okay.
The pointer.
Oh.
Pointer. Just point. You have to use the key.
Okay. This one. Okay, let me see. Okay, now. So here is the outline of the talk. So in Professor Wang's talk, we have already seen the results of Xi and Tan and Wang Miao have been used in a critical way in the productivity of the most recent definition of Wang Yao colligible mass. Here I give a relatively detailed review of their theorem, and then I will talk about some observations, some observations regarding the total mean curvature, which allows one to talk about a variational analog of Brownian mass. And such a variational analog of Brownian mass is really a look at the total mean curvature from a GR point of view. So in the third of my talk, I'm going to look at the total mean curvature from a purely geometric point of view. So that's the outline of my talk. So first, the Xi-Tan theorem. I know many audiences here are very familiar with their theorems and their proofs already. But for the benefit for those of you who are not familiar, let me give you an outline of their proof of their result. So first of all, so the object here is a compact connected Riemannian three-manifold with non-negative scalar curvature and with non-empty boundary. Assuming the boundary has finitely many components. So here, either you have a connected boundary, or the boundary may be disconnected. But in the theorem, one always assumes that all the boundary components, they have positives. So first of all the boundary components are topologically two spheres. Second of all, the induced metric are assumed to have positive scalar curvature. And then there is a condition imposed on the mean curvature. Here the sign of the mean curvature means the mean curvature vector on the boundary of the manifold always points inward. Now, under the assumption that the induced metric on each boundary component has positive Gauss curvature by the solution to the Val's embedding theorem, which is due to Nuremberg and also Roloff, one knows that the boundary, each boundary component can be isometrically embedded in R3. In particular, one can talk about the mean curvature of the isometric embedding of the boundary sigma embedded in R3 versus the mean curvature of sigma in the original physical manifold. And the result of the theorem is really a comparison on the total mean curvature. So it says the total mean curvature of the boundary in the original physical manifold is always less than or equal to the integral of H0. And moreover, the rigidity part says if the equality holds for one boundary component, then the boundary, first of all, it must be connected second of all, the whole manifold must be isometric to the domain enclosed by the image of this isometric embedding. In particular, omega must be isometric to a convex domain. Now, there are a few ingredients in the proof of this theorem. The first one I already mentioned, which is the solution to the Miao embedding problem. That's where this positive Gauss curvature assumption is used. So that's one key ingredient. The second ingredient is a quasi-spherical type construction proposed by Barnick. So there, by Barnick's quasi-spherical type construction, one deformed the Euclidean metric on the exterior of this of the image of this isometric embedding. So by performing a quasi-spherical type metric construction, one deformed this exterior Euclidean metric, and then one attach this newly constructed asymptotically flat end to the original manifold, so that one get an asymptotically flat manifold whose metric may possibly be non-smooth across the original surface. And there, one applied the positive mass due to Shen and Yao, and also later proved by Witten, to conclude that the mass of this fluid manifold is actually non-negative. So the positive mass theorem plays a key role here. Another ingredient is a monotonicity formula, which shows the difference of the total mean curvature of the Euclidean embedding minus the total mean curvature of all the leaves, which corresponds to the level set of the distance function to the original image, is actually monotone decreasing to the ADM mass. So combining those ingredients, one concluded this comparison of the total mean curvature. So this is the result of manifolds with non-negative scalar curvature. And then Professor Wang and Professor Yao later they derive the corresponding result for manifolds whose scalar curvature are allowed to be negative. Let me draw the corresponding picture on the other side, on this part of the board. So here one has a compact free manifold, again with boundary. And this time the scalar curvature is allowed to be negative. Say it has a lower bound of negative 6 times kappa squared. And moreover, assuming that the boundary is a topological two-sphere whose Gauss curvature satisfies the corresponding lower bound, k is greater than or equal to negative kappa squared. And under this assumption, first of all, by the theorem of Pogorelov, this boundary can be isometrically embedded into the corresponding hyperbolic space of constant sectional curvature negative kappa squared. Now, if one identify this hyperbolic space with the hyperboloid in the Minkowski spacetime, one see that this isometric embedding of the boundary surface into this hyperbolic space can be viewed actually as a map from sigma into the Minkowski spacetime. And what Wang and Yao proved is there exists, so under such a condition of a scalar curvature and the boundary geometry, there exists a future directed time-like vector values function defined on the boundary sigma with value in the Minkowski spacetime. Say W0, such that if we consider this vector value the integral of h0 minus h. Now what's h0? H0 is again the mean curvature of the image of the isometric embedding of the boundary into So here, in this picture, one see there are two vector value map involved. One is which I call iota, which denotes the isometric embedding of the boundary. Another one is this vector value function produced by the theorem. And the conclusion is this vector value function is future-directed line spacetime. And here, W0 depends on the isometric embedding, iota, which itself depends on the induced metric on the boundary, and also this W0 depends on H, where H is the mean curvature of sigma in omega. And later, so after this result was derived, later Xi and Han made this observation. So if one goes to this picture, naturally one may wonder what would be a simplest choice of choosing this W0. So maybe let's go back to Miao theorem first. So what would be a natural or simple choice of this W0? In this picture, we already have such a vector value function given by the embedding. So naturally, one may ask, could W0 be chosen as iota, which can be written as x1, x2, x3, t, which simply denotes the position vector function. So can we choose that? And later, what Xi and Han observed is you can almost do that. You can almost do that, except you need to insert a constant alpha, where alpha is a constant which is strictly positive, which is strictly bigger than 1. On the other hand, alpha depends on the intrinsic geometry of sigma alone. So that with this choice of W0, the previous theorem holds as well. Now, in particular, this is a vector valued function. In particular, one can focus on the time component. If one focuses on the time component of this vector value function, one see that cosh kappa r shows up. So that allows them to derive the following comparison of a weighted total mean curvature. So again, under the same scenario, one conclude that the integral of h, where h is a physical mean curvature with this weight, cosh kappa r, where r is the distance from the image of this isometric embedding to any fixed point in the interior enclosed by the embedding in the hyperbolic space. So this weighted integral is always less than the integral of the corresponding quantity with h replaced by h0. In particular, that kappa goes to 0. This result recovers the first theorem in a non-negative scalar curvature case. Okay, let me give another remark regarding the theorem of Wang Yao. So even though Wang Yao theorem was stated in the paper only for manifold with one boundary component, well, actually they do state it in the paper that the same conclusion holds for multiple boundary components as well, as long as the corresponding assumption holds. So in other words, their theorem applies well to a configuration with multiple boundary components. And in fact, by a result of Crucial and Kurzlik, indeed, if one goes through the same proof, one observes that the same conclusion holds as long as the remaining boundary components of such a manifold, say in case you allow other boundary components to appear, so as long as the mean curvature of the remaining boundary component satisfies the corresponding inequality, h bigger than equal to negative 2 kappa, then the same conclusion holds. So that's a remark on today. Now let's return to the original context of Xi-Han theorem, which is a conclusion regarding manifold of non-negative scalar curvature alone. here, here the scalar curvature is assumed to be non-negative, and sigma is a topological two-sphere having positive mean curvature. Naturally, one may wonder, so if one drops the assumption that sigma has positive Gauss curvature, what can be said regarding this total mean curvature? So without assuming h k is positive, we lose the isometric embedding of the boundary into the Euclidean space. So we ask, is there any information regarding this total mean curvature? As long as we assume the scalar curvature is not negative, and technically we are also willing to assume that the mean curvature is positive. And here is a direct observation built on the previous results of Wang, Yao, and Shitan. So the claim here is, in such a configuration, as long as the manifold has non-negative scalar curvature and the boundary has positive mean curvature. So here we do need to still assume that the boundary is a two-sphere. So far, we always assume that the boundary is topologically a two-sphere. Then the claim is there exists a constant depending only on the induced geometry on S2, so that this quantity has this upper bound. And as I said, this is a direct observation built on the previous result of Wang, Yao, and Shitan, which I will give you, which I will explain why. So under the previous assumption, first one can choose. Okay, so to choose a constant kappa so that the Gauss curvature of this metric satisfies this assumption. One can always do that. And then the fact that the scalar curvature is not negative implies that for this given constant kappa, one has this estimate. Now, if you have other boundary component which satisfies h greater than or equal to, well, I think for this part we do not need to worry about that. So let me just make the story simple. So assuming there is no other boundary component, then one can apply Wang Yao's theorem so that one has this picture of the isometric embedding of the boundary into a corresponding space form or hyperbolic space. And in particular, one can apply Shitan's estimate to get this comparison of the weighted total mean curvature. Now, this quantity has nothing to do with this quantity is completely determined by the embedding. So it depends only on the induced metric. And here, the left-hand side obviously has the following estimate. Say one can choose the minimum value of the function of r, where recall that r is the hyperbolic distance from the image of the embedding to any fixed point. Say we choose r star, which is the minimum value of this distance function, then immediately one obtains this estimate. Where this r0 certainly also depends on the induced metric as well. So that explains why one has this lower bound, has this upper bound. And I want to comment that this observation was, we recently learned that this observation was also used by Lu in his work on isometric embedding. The way that we learned this is my collaborator Christos Matolidis was actually at the center a month ago in another conference in which Professor Guan Fei has talked about Lu's work. So that's how we learned that Lu also made this observation. Okay, next. So consequently, one can have the following consideration. So we take our surface to be the two-sphere, and given any metric gamma, one can consider the following set. The set of F sub sigma gamma so that the boundary is isometric to the prescribed surface S2 endowed with the metric gamma. And we also impose the assumption that the mean curvature is positive. And then the previous observation translates into the following statement. Then, if we define, say, this lambda sub sigma gamma to be the supremum of this total mean curvature normalized with this normalizing constant, then regardless of what this omega g is, for example, the different omega may have different topology, as long as the scalar curvature is not negative, as long as the boundary is isometric to this prescribed surface, then this supremum of the total mean curvature is finite. And by definition, this supremum is an invariant of the metric alone. Given any metric gamma, you have this finite invariant. Here is the remark. It's natural to wonder, what about the existence of elements in this set? So in other words, here you define such a set. Is this set empty or not? Now, the first sufficient condition to guarantee this set to be non-empty might be to assume that the Gauss curvature to be positive. So if we go back to the original case where the Gauss curvature is positive, then the surface can be isometrically embedded to R3. So we have the Euclidean domain, the Euclidean domain enclosed by the isometric embedding. So in particular, this set is not empty. Now, in fact, there is a weaker condition than the positive Gauss curvature condition. In fact, given a metric on S2, if one assumes the first eigenvalue of negative Laplacian plus k is positive, under this assumption, then by applying the method of Matolidius and Shen in one of the recent paper where they studied the Barnick mass for apparent horizons. So apply the method in that paper. One knows such a set is not empty under this weaker assumption. In particular, this assumption allows the metric to have negative Gauss curvature. So that's a remark regarding the set F. Okay, so
Their sigmas were minimal.
In a sense, in the case of Barnick mass,
Yeah.
right? Okay.
Even stable.
Yes, that's the motivation. So if you have a stable, if you have a stable minimum S2 in a positive scalar curvature antimetric, then that implies the positive lambda 1.
But the condition could be much weaker.
The condition, in general, if you have a stable minimum surface in a non-negative scalar curvature metric, that implies lambda 1 is non-negative. So they were able to handle the strict positive case. If lambda 1 is 0, then the method does not apply. So conceptually, the previous observation may be tied to the classic definition of Brownian mass, which appears in the previous part. So here, suppose the boundary two-sphere has positive Gauss curvature, then the Brownian mass of sigma computed in this space-like hypersurface or in this ambient three-manifold is given by this integral, the integral of the difference between the mean curvature of the embedding and the physical mean curvature. Now here, a basic fact is, even though one made use of the existence of the isometric embedding under the assumption of the positive Gauss curvature, the isometric embedding is used only to an extent that it's the total L1 norm of the mean curvature of the H0 is used. So in other words, one does not use H0 in a point-wise way in this classic definition of Brownian mass. Only the integral of H0 is used. So with this in mind, it's natural to have the following consideration. Given any metric, without assuming the metric has positive Gauss curvature, given any metric, we already know that lambda, sigma, gamma, this invariant is finite. Therefore, one can consider the difference of this invariant, which only depends on the induced metric on the boundary and the corresponding physical photon curvature. So this quantity is defined for any complex manifold whose boundary is a two-sphere. At this stage, going back to Greg's remark, yes, in this case, so in spirit, this is an analog of Barnick mass in spirit. In the Barnick mass case, one consider infimum of the ADN mass. Here, one consider the supremum of the photon curvature. So in that sense, yes. And immediately there are a few obvious properties that follows from the definition. So assuming the physical manifold has dynamic scalar curvature and positive mean curvature, so that this physical manifold falls into the set of competitors, then by definition, this quantity is dynamic. So that follows from the definition. Second of all, one can prove that this quantity is zero only if omega g is flat. In fact, here more information can be said. So this quantity is zero only if, because we are assuming the boundary is a two-sphere in this case, one can show omega g is a handle body, is a flat handle body whose boundary is S2, and therefore, topologically, it's a three-fold. And if the Gauss curvature is indeed assumed to be positive, then this quantity agrees with the Brownian math. And this third property is simply another way to state that Schittan theorem. So in other words, Schittan theorem says if K is positive, then this invariant is computed by the total mean curvature of the integral of the Euclidean mean curvature. Okay, so far we are focusing on the GR aspect of this observation, where this total mean curvature is bounded from above. Before we move on to the geometric aspect, here is a remark. Instead of working with this class consists of three manifold omega whose boundary is a given surface, one can also enlarge this class. One can also enlarge this class so that the class consists of omega g, whose boundary consists of other pieces where the other pieces are minimum surfaces. So in other words, given a surface which is S2 endowed with a metric, one can also consider those compact manifolds whose boundary, except the given sigma, the remaining part of the boundary consists of horizons. By definition, this set is larger, and if you consider the supremum of the total mean curvature over this larger set, indeed one can show that those two supremums are the same. So in particular, in the previous definition, one can also use this larger set. Okay, next I want to move on to this geometric aspect. What do I mean by the geometric aspect? I think from the GR point of view, it's more reasonable just to focus on a single boundary component. But here, naturally, one can consider a configuration corresponding to the multiple boundary components in the previous theorem. So let's start with a finitely many closed, connected, orientable two surface, sigma 1 up to sigma k. And let's start with let's endow each surface with a corresponding remaining metric, the gamma j. then one can consider this set F sub sigma 1, gamma 1, up to sigma k, gamma k. So one consider the three compact manifold omega g with whose boundary is isometric to the disjoint unit of the collection of the initial Riemann surface, and satisfying the assumption that the curvature is positive and the scalar curvature is positive. And formally, one can consider the supremum of the total boundary curvature. Now, if this set is empty, because now the boundary can have different topology, a priori we do not know if the set is non-empty. If the set is empty, one defines this supremum to be negative infinity. So in this notation, Chitan theorem translates into the following. If each surface is a two-sphere with positive Gauss curvature, first of all, the theorem says if we look at this single lambda, if we look at this lambda with a single pair, sigma, gamma, j, then this supremum is realized by the corresponding integral of the Euclidean curvature of that boundary component. Second of all, the theorem says in this multi-boundary component configuration, if one focused on the integral of the mean curvature at a particular boundary component, then this integral must be less than equal to the corresponding lambda with this single piece. So this is just a translation of their result in terms of this notation. Okay, with this in mind, one can prove a formal a statement which is a formal analog of the previous Chitan theorem. The reason this is a formal analog is because, again, because a priori we do not know whether this lambda is finite or not if we allow the boundary to have non-spherical topology. Okay, let me explain what this claim means. So suppose we have an element in this set, then the claim is if you pick a boundary component, then the total mean curvature of that particular boundary component it must be bounded from above by the corresponding lambda associated to the set F with sigma j, gamma j alone. In particular, we recall that this lambda is defined to be the supremum of all manifolds whose boundary consists of sigma j alone. So even though originally you may start with a manifold with multiple boundary components, but if you focus your attention to one boundary component, you still have this density, which formally appears in Chitan's theorem. Now this theorem is a vacuum. Notice that this inequality is a vacuum for k equals 1. If k equals 1, there is nothing to prove because lambda is defined to be the supremum. So for this inequality to be meaningful, it's really a statement for manifold with multiple boundary components. The rigidity case does have content for the regardless of k. So here the rigidity statement says if the total mean curvature at one boundary component equals the supremum of the corresponding lambda, then that occurs only if this manifold. So first of all, k equals 1. That occurs only when the boundary is connected, and moreover, that occurs if this omega g is isometric to an inconvex handle body with flat interior. In particular, because the boundary is shown to be connected, the genus of this handle body is the same as the genus of the boundary. If the boundary is an S2, then this manifold is topologically a through ball. Another thing that can be said regarding this functional is, in fact, one can prove this additivity property. So by definition, this lambda, the lambda with this long subindex is the supremum of the total mean curvature of all the configurations like this. Here one can show this supremum actually splits into the sum of the supremum of all the configuration of manifold with a single boundary component. And this can be shown provided each the corresponding set f sub sigma j gamma j is non-empty. So in fact, in the proof, one see the set consisting of all such configuration is empty. That case occurs if and only if one of the corresponding set with respect to a single boundary component is empty. So in other words, if every initial Riemann surface admits such omega g in the corresponding set lambda sigma f sigma j gamma j, then the corresponding set f with this long index is non-empty. I think I will give an outline of the proof, but first I will also mention this technical lemma used in the proof. So the lemma says, if sigma is a closed connected orientable surface with a Riemann matrix, suppose we take an element in this larger class. So in other words, either omega g has only one boundary which is isometric to the prescribed sigma with gamma, or it may have other minimum surface boundary component. Now, assuming each boundary component is a stable minimum two-sphere, assuming the ambient scalar curvature is positive along those spheres, in fact, the third condition is only imposed to make sure that lambda 1 of each minimum sphere is positive. Now, under this assumption, basically, the concurrence says one can close them up. So, under these boundary assumptions, one can close them up in such a way that the total mean curvature changes in an infinitesimal way. Now, intuitively, this is very doable. Intuitively, to make the construction precise, one makes use of the previously mentioned Methodist Shen method to make use of the positive lambda 1 condition to do this construction. Now, to end in the end of my talk, let me give an outline of the this claim. First, let's say we want to show the greater than equal, the direction that this quantity is greater than equal to the sum of these two. So for each initial surface, assume all the set is non-empty. Then one can take a compact manifold omega j for every j, so that all the scalar curvature is always non-negative. And then the idea is to do a connected sum. Now, to do that, technically one wants to make the scalar curvature to be positive. So by applying a conformal definition with the conformal factor being 1, say next to the boundary, one can make the scalar curvature actually positive in such a way that the mean curvature at the boundary changes in an arbitrary small way. And once the scalar curvature is positive, Lawson construction to construct an element in the corresponding set.
If we did experiment myself, not remove a Lawson. It's kind of funny, you're a student. We did it 1 year for them.
But the construction needs to be local, right?
The construction is local, yes.
Oh, this can be done locally. Our argument is to can done locally. You can do a small deformation.
Yes, one time. Right. So yeah, the conformal so if one apply conformal deformation, one raise the scalar curvature up everywhere. But as long as you have positive scalar curvature everywhere.
Yeah, you can do that.
Yes. I should make the reference more precise. Now, okay, this gives us the direction of this inequality. On the other hand, to see the other direction, one use the lemma we just mentioned. So again, technically one want to first bump the scalar curvature up so that one have a positive scalar curvature configuration. And then, because the mean curvature vector at each boundary component points inward, one can consider a surface that minimizes area among the homology class with respect to the boundary component. And moreover, for technical reasons, one can first start with a configuration assuming this manifold is orientable. Assuming this manifold is orientable, with the scalar curvature deformed to be positive, then if one consider this corresponding area minimizer, we know this is a stable minimum surface which is orientable because we assume that any manifold is orientable, and the any manifold is deformed to have positive scalar curvature. So one concludes this surface consists of minimum S2 with positive lambda 1. Oops. And then one apply this lemma to close everything up. So one do this, one apply this construction for each component, and this explains the other inequality. So basically, this idea is very obvious to. This is an obvious picture. So all we do is to make this construction precise using this fitting in construction. And to end my talk, I'll just list some immediate questions. So first of all, if you take a surface which is not S2, is it true that this supremum is still bounded? We really have no idea about this one. And second, even if this supremum is finite, say in a special case, if this initial surface can be isometrically embedded in R3, then does this supremum achieved by the corresponding Euclidean total mean curvature? One knows this if sigma is S2 and gamma has positive mean curvature. One only know that in this special case, but in general, it is true. Think I'll stop.
Are there any comments, questions for the speaker?
So do you have examples where this is not equal to the norm of H naught?
Yeah, and that's even to even get an example.
It's not positive Gauss curvature. There could be different isometric embedded. So the mean curvature, we talk about integral H naught, like they may not be unique.
But since he's taking the supremum, then he will pick the.
Maybe one of them. Yeah.
So it could be that your mass is actually the same as Brownian.
Yeah, I mean, say in the positive Gauss curvature case, they agree.
Yeah,
Now,
but in general.
in general, Brownian mass, precisely speaking, is not defined if you drop the positive Gauss curvature condition.
Other questions? Okay, now this concludes today's session. We'll meet again tomorrow morning at 9 o'clock. That's next week.
So your Miao argument,
No, you can, because
with the manifold of magnetic valve.
basically,
Yeah.
Boundary conditions later on this week?
yeah,
Wednesday?
Wednesday.
Wednesday after the seminar?
Maybe tomorrow.
Yeah, that sounds very good. So we shall meet tomorrow?
I'll be here all day.
Right.
Should we first in the morning?
Right. We can talk after.
这一次要做好，
No, but I mean,
有的时候要好几年，有的时候也还比较想明白了之后，
是啊，你想明白的东西就很快。你要是没想通，不知道怎么理，过了一会儿好像有开始有灵感，你好像觉得好像走上正路，然后慢慢一点点往前走，你越可能会越走越快。你是在这边吗？你是这边吗？它这个都是这样，像我以前。
Yeah, and then there goes back part.
The initial yes, so apply this theorem, you have Pengzi Miao. Let's do use their theorem directly. So for h equals 0, they have this curvature. Yeah. One could do that. One could use their result. So for h equals 0, they produce this which is the new identity structure. Now one has
So if you walk down Garden Street,
there's something going on here. Exact structure at the end.
If there's something going on here, I'm most likely to hear.
So the claim is one can deform this conformal factor
this makes no
so
sense
that
that you just walk right
but
up.
you can make this
It's like,
part
yeah,
of the
you
sphere.
walk north. Yeah, I'm
You're
gonna say.
keeping the magnetic scalar curvature.
I was just orienting. Yeah, that's not the way I would recommend walking.
If that's the
Just
case,
orient you.
you have this compact manifold with magnetic scalar curvature with positive scalar curvature somewhere. Well, in fact, in their argument, the scalar curvature is called Chapter policy. But anyway, you have this configuration.
And you
Then
eventually
do
get
a
mass
conformal
out, which
definition
is
to bring the scalar curvature down.
impossible to miss it.
The conformal definition.
It's called root 2 or something like that.
The conformal definition. That's the conformal definition. So
I don't know this part first very well, but probably.
Should I bring my bag back to the friendly inn and come back, or should I bring?
Sorry? Good, it's good.
and if you do that,
You're getting better.
The restaurant
I told you about the way our year long next week. I'll show you.
So that's called U. U equals the original H plus is constant. Where show me where you do function.
By the way, this is something I'm not about H so much.
It's getting better, yeah. So
And I really?
And H column means
I didn't say all these
far as I'm concerned.
Yeah.
Misunderstand your entire talk.